This is linear algebra, lecture 5. In section 1.5 on homogeneous equations. And we start with first the idea of translation. So we have a vector space V and a subset X contained in V, and a vector V in V. So what we call the translate of X by the vector V is just the set that's written as V plus X. It's a set of vectors, and it's all vectors of the form little v plus little x, where X is in the set X. So you take every vector in the set X and translate it by V. That is, you add V plus X. This is what one calls the translation of the vector X by V. And the most important case is if W is a subspace of the vector space, so not just any set, but a set that's a subspace, then the translate of W by the vector V is what is called an affine subspace. It is an affine subspace of V. So this is the new word, well, I guess there are two new words that we're introducing here. One is translate, and the other, a special kind of translation, is an affine subspace. So let's just take an example. And if you study the example, you'll see how easy the concept is. Suppose we let V be the ordinary XY plane, the vector space R2, and W to be the subspace consisting of all scalar multiples of the vector 1, 2. In other words, this is a set of all vectors that can be written in the form X, 2X for any value of X. And if we let V be equal to the vector 0, 3 in R2, we have the affine subspace, let's call it L, which is V plus W. This is the vector V, this is W. So that's the vector 0, 3 plus the set of all vectors of the form 1, 2. Well, if we do this addition, this is this is X 3 plus 2X. Or let me write that as 2X plus 3. For X and Y. Or again, we can write this as the set of all vectors X, Y, where Y is 2X plus 3. So let's just draw a picture of what this is. So here we have the vector space R2, and W is the set of all scalar multiples of the vector 1, 2. It's just this line, Y equals 2X. This is all vectors, X, Y, where Y is equal to 2X. It's the line Y equal 2X through the origin. That's the one-dimensional subspace, W. And what is the affine subspace L? It's just all points on the line Y equal 2X plus 3. So this is an equation with the same slope 2, but Y-intercept 3, 1, 2, 3. This is L. This is the line Y equal 2X plus 3. So if you take your subspace W and you translate it by 0, 3, that means we're translating it up 3 units. we get a line parallel to the original line. This is the original line, y equal 2x. And the affine subspace is just a line, not through the origin, it's not a subspace, parallel to the subspace of the line y equal 2x. And affine subspaces arise very naturally when we're studying inhomogeneous equations. When we study homogeneous equations, the solution is always a subspace. When we study inhomogeneous equations, the solution is not a subspace, but it is a vector subspace. Sorry, it is an affine subspace. So let's look at some examples. So let's start with the homogeneous equation. (3x1 minus 2x2 plus x3 equals 0. So what is the solution space? So the solution space, W, if you solve this equation for x3, you get x3 is minus 3x1 plus 2x2. So the solution space is all vectors of the form x1, x2, minus 3x1 plus 2x2 for any scalars x1 and x2. This is the solution space. And we could write this if we like. If we separate this into the pieces that involve x1 and x2 separately, this is all vectors of the form x1, 0, minus 3x1 plus 0, x2, 2x2 for any x1 and x2. Or if I factor out the x1 and the x2 from these vectors, this is all scalar multiples of the vector 1, 0, minus 3 and 0, 1, 2. So this is a subspace. It's the solution of the homogeneous equation. Suppose we look at the inhomogeneous equation. So this is the equation when the right-hand side is not 0. For example, 3x1 minus 2x2 plus x3 equals 6. And this equation has a lot of solutions. For example, particular solutions, just examples of solutions. But at x1 equal 1, x2 equal minus 1, and x3 equal 1, I get 3 plus 2 plus 1 equals 6. So one particular solution of the inhomogeneous equation is 1 minus 1, 1. An even simpler solution would be to take x1 equal 2 and x2 and x3 to be 0. Or I could take x2 to be minus 3 and x1 and x3 to be 0. Sorry, this should be a 2. 2 times 3 times 2 is 6. Or more interesting solutions, I could take x1 to be 9, x2 to be 8. Let's see, this would be 27 minus 16. 27 minus 16 is 11. Minus 5 would give me 6. Or I could take 0, 3. This is 0 and this is 3. This is minus 6. So I have to add 12 to get plus 6. So these are just particular solutions of this equation. Right? There are lots of solutions. There are infinitely many solutions, in fact, and we want to describe them all. So again, we can solve for one of the variables, and because in the equation 3x1 minus 2x2 plus x3 equals 6. x3 occurs with a coefficient of 1. The simplest thing is to solve for x3. x3 is minus 6. Sorry, x3 is 6 minus 3x1 plus 2x2. If I let L be the solution space of this equation, for any values of x1 and x2, x3 has to be 6 minus 3x1 plus 2x2. It's all such vectors for any x1 and x2. And I can separate this as this is the vector 0, 0, 6 plus the vector x1, 0, minus 3x1 plus the vector 0, x2, 2x2 for any values of x1 and x2. So I can write this as all vectors of the form 0, 0, 6 plus x1, oops, factor out the x1. This vector is x1 times 1, 0, minus 3. This vector is x2 times 0, 1, 2. And I can look at the whole set of vectors for any values of x1 and x2. So this is exactly the solution space of the inhomogeneous equation. This is that set W that was the solution of the homogeneous equation. This is 0, 0, 6 plus W. So this solution space is an affine subspace of V. And of course, just make a note, if W is a subspace, then if I translate W by the 0 vector, I just get back W. So W is also an affine subspace. And we can observe that an affine subspace is a subspace if and only if an affine subspace L, an affine subspace L is a subspace if and only if the 0 vector is in L. If your affine subspace is a subspace, of course, it must contain 0 because every subspace must contain 0. So if your affine subspace is a subspace, it contains 0. On the other hand, if a subspace does contain 0, let me actually make it on the side, move this back. So this is part of the proof. Let L equal V plus W be an affine subspace. Where V is in V and W is a subspace of V. If L is a subspace, I'm sorry, if 0 is in L, then there exists a vector W prime in W such that 0 is v plus w prime. Because everything in L is v plus something in w. So if 0 is in L, 0 is v plus something in w. But this implies that minus v is equal to w prime, which is in w. Which implies that actually, I should have said it. V is equal to minus w prime, so v is a vector in w, which means v plus w is in w for all vectors in w, which means v plus w is contained in w. And w is contained in v plus w, which means my affine subspace L is equal, which is v plus w, is equal to w, is a subspace. So if an affine subspace contains 0, then it's actually a subspace. So that's the little map. And the general fact, of which you've just seen an example, is, so this is the big theorem in this section. The solution space of a, I should say, inhomogeneous linear equation a1x1 plus a2x2 up to an xn equal b. Of course, non-zero, some of the a's, not all the a's can be 0. So the solution space of the non-zero inhomogeneous linear equation is always an affine subspace of v. It is a subspace of v, a vector subspace of v, if and only if the equation is homogeneous, which means if and only if v is 0. And the proof goes as follows. It's called the solution space L. So every equation, every non-zero equation has a solution. So that L be the solution space of the equation. And L is not equal to the empty set. This is the empty set. That's the set with nothing in it. This means that there is a solution, a vector, v, with coordinates v1 to v sub n in L. There's some solution of this equation. If we consider the homogeneous equation, so in the solution space of the homogeneous equation, a1x1 plus a2x2 plus anxn equal to 0 is a subspace W of the vector space. So if some vector W with coordinates x1 up to xn is in W, that is the solution of this equation, then what can we say? Well, we have A1 V1 plus A2 V2 up to AN VN equals B, because V, which is the vector V1 down to Vn, is a solution of the inhomogeneous equation. And we have A1 x1 plus A2 x2 plus AN xn equals 0, because W with coordinates x1 down to xn is a solution of the homogeneous equation. What happens if we add? We get A1 V1 plus x1 plus A2 V2 plus x2 plus AN Vn plus xn equals B plus 0 is B. So therefore, V plus W, which is the vector V1 plus x1 down to Vn plus xn, this is in L. So what this says is, if I take the vector V and add it to any vector W in W, this whole set, this whole translate of W by V is contained in L. So L contains V plus W. Conversely, if V prime with coordinates V1 prime down to Vn prime is in L, then A1 V1 prime plus AN Vn prime is equal to B. This is another solution of my equation. And V was a solution, so we also had that A1 V1 up to AN Vn is equal to B. And if I take these two equations and I subtract, I get A1 V1 prime minus V1 up to AN Vn prime minus Vn is B minus B. I'm subtracting this equation from this equation is 0. And that means that the vector with coordinates V1 minus V prime down to Vn minus Vn prime, that's the solution of the homogeneous equation. So this is in W. This is the vector V prime minus V. Or another way of saying that is that V prime is in V plus W for all vectors V prime in L, which means L is a subset of V plus W. So you have V plus W is contained in L, and L is contained in V plus W. And if I put those together, I get L equals V plus W. And that's what I wanted to prove. The solution space of the inhomogeneous equation is an affine subspace. It's a translate of the solution space of the homogeneous equation, that's W, by the vector V, which is a particular solution of the inhomogeneous equation. And that is the important fact in section 1.5. So that's the end of this. And in the next lecture, what I'm going to do is solve the various homework problems in chapter 1, so you see the solutions worked out got in front of you. That is it.